one-dimensional layer of qubits. So this is x direction. And I study the dynamics when I couple the two qubits together with some random unitary. And people call this geometry brickwork geometry. So I couple pairs, and on the next layer, I couple the other pair, and so on. So let's forget about a measurement for a second, and let's study the steady state in the system. So in the absence of measurements, so when these dots are absent, in the steady state, the steady state is very quantum, so it has lots of entanglement. Namely, if I pick up, say, some interval A of qubits, this can be called A. Then the von Neumann entropy of this subsystem, it will be proportional to the number of qubits in A. So this is what you will call volume law entanglement in one dimension. By the way,
excuse me, could you remind briefly what are the qubits and what does it mean measurement and something else?
So now there are no measurements. So now let's forget about this for a second, and let's study these dynamics. So a qubit, it just means that it's a two-level quantum system. So like each line here, if I take a slice, a time slice, then in all intersections here, I have a two-level quantum system with either 0 or 1. This is what might be called qubit. Yeah, please, if there are any questions, just stop me anytime. Don't even apologize. Yeah, this is just, you know, a toy model for a quantum computer. So we don't study any specific quantum circuit. We just study a generic one where all operations are random. Okay, let me now add a local measurements. So what does it mean? So it means that when I look at the evolution, so suppose I'm like at on this slice t = 1, then I go from qubit to qubit, and with probability p, I perform a measurement in the z basis. So what does measurement mean? So for measurement in the z basis, I can introduce projection operators, which is 1 plus sigma z. So this is p plus and p minus 1 minus sigma z. And then measurement means that I collapse my wave function. So with probability, so what's the probability of measuring spin up? The probability of measuring spin up would be this. Okay. So with this probability, absolute value squared, with this probability, I collapse my wave function. So so with this probability, my wave function becomes I projected on a eigenstate with where spin is up, and I also normalize the wave function. So I normalize by this probability. Yeah, this is how projective measurements are described in quantum mechanics.
Excuse me, I don't understand. What means that this is a projector? It is Z is a complex number or what?
It's an operator. So if I divide it by square root of 2 or something, p plus squared is equal to p plus. It's a projector in the sense of linear algebra.
And what is the Z operator?
It's Z. It's Pauli Z.
I see. Thank you.
So does it mean that the probability is equal to 1 or 0, according to this formula? Or is it right?
Probability is between 1 and 0.
Why? P plus project on the state with a spin up, for example. So if psi is not state with a spin up, it P plus acts by 0. Is it right?
Yeah, but you can also have states which are alpha 0.
I see.
Beta 1.
Okay, yes. I see. Okay. Okay, thank you.
And then, yeah, this formula is just, for example, for P plus, it will select absolute value of beta squared. I mean, the usual, Born rule.
Okay. Thank you.
So yeah, it is. It's a toy model for noisy environment of your quantum computer that it interacts with some classical environment. From time to time, it causes the wave function to collapse on a specific state. Okay, let me prove in quotation marks, because it's actually not a valid proof. Why? So any projection rate, so I have projection rate P, any projection rate greater than 0 will destroy the volume law phase of entanglement. So consider like one cycle of applying the layer of unitaries, then layer of projections, then layer of unitaries again. So at some on some layer, I have volume law entanglement. So I again pick up some region A. So on different slices. But stay on slice 1, I have a volume law entanglement in that state. Then on average, yeah, since I'm taking each qubit and projecting it with probability P, on average, I will project P times A qubits in that interval. And projected qubits, they're not entangled anymore with anything. So they just end up in either 0 or 1, and they completely lose any entanglement with the other qubits. So since I projected the finite fraction of them, like the fraction proportional to volume, the entanglement entropy will also reduce by order volume. So there will be some, for small p, say it will be linear, and there is some extra, I don't know, phenomenological coefficient kappa, which says that, okay, the entanglement should decrease by amount of volume, and also it should be proportional to P. Okay, so,
Excuse my ignorance. What is S of A? What is its definition?
it's a von Neumann entropy. So I consider, so I have a state psi, yeah, on the whole slice, okay, on the whole thing. Then I can form a reduced density matrix, rho A, which is when I trace out the complement of A. Okay, and then S of A is minus
Something got wrong with the presentation. Distorted.
Can you hear me still? I think my laptop is just died.
Okay.
Now I can hear you.
Sorry, just a second. I have a problem with a laptop. Okay, am I back? Can you still see my screen and the annotation?
Yes, yeah, everything is visible.
Okay, good. Okay, so yeah, the von Neumann entropy of A, it's basically the usual entropy for the reduced density matrix. So trace rho A log rho A. So it's for pure states, if the total state is pure, this is a good notion of, I don't know, quantumness or entanglement between A and its complement. So for example, if you take Bell state or APR state, again, I'm like, for the sake of not writing too much on the screen, I'm omitting normalization. So for one of the qubits, von Neumann entropy will be log 2. So I leave it as an exercise. And for a product,
and here A is some subsystem of qubits, right?
yes, yeah, that's right.
Okay, thank you.
Yeah, if A and the A complement are in the product state, then von Neumann entropy is 0. Otherwise, it's positive. Yeah, here it's a little bit heuristic. I'm just saying that you can imagine that you have like A, and you have these qubits which are entangled with the qubits outside. So okay, this is A, and like as a toy model, you can just imagine that this qubit in some Bell state in the maximal entangled state with this other qubit, and then when you project, when you do a measurement, this entanglement is gone. So now you end up with this qubit being in some specific state up or down. And this is why the entanglement will also decrease by amount proportional to A. And it's very bad because in the next layer of unitaries, say, okay, here I projected, so say this is A. Okay, no, maybe it's not good. Let's call, say, for example, this is A. Okay, if this is A, then this next unitary here will only entangle. I still don't like this A. Let me draw it bigger. Let's call this A. Okay, this one, this A is representative. So this A, I projected it, but then the next layer of unitaries, it will only entangle the boundary qubits with the outside. So only these two unitaries actually will matter for entanglement. So you can check that if you have some state on A, and then you act with a unitary matrix just within A, it doesn't change the entanglement. So this is row A tilde, then this one and this one, they have the same entanglement. So all unitaries inside A, they don't matter for entanglement. And it means that the entanglement can only increase by a constant amount independent of the size of A. And it's very bad because, so it is just one cycle, right? So if after 2 cycles, I have to put, factor of 2 here. After 3 cycles, I will put factor of 3. So it becomes clear that in a steady state, I cannot have volume law entanglement because after each cycle, I decrease the amount of entanglement by volume law amount because of this kappa p, but I increase it only by order 1 amount. So, are there any questions? So this proof, it is not correct. So one of the 3 is actually is not true. So maybe someone would like to guess which one is not true.
The last one.
Okay, any more guesses? So, okay, as usual, experiment is the, criteria, what is really going on. So people did this experiment. So this was done numerically in this paper. And they found that volume law entanglement phase, it persists very well for finite amounts of measurement rate. So there's of course some critical one. If I measure too much, then yeah, I don't have volume law entanglement anymore. But if it is below some critical amount, then that's fine. And actually, it is equation 2, which is not correct. So in fact, you can measure a finite fraction of qubits, but the volume law coefficient S, it will remain the same. It is not obvious, and there is a paper which I really like, which links that to emergent quantum error correction in these random quantum circuits. So the upshot of all this is that interestingly, quantum systems they can often resist noise coming from decoherence. So decoherence does not happen gradually as you increase the noise ratio. Instead, it happens like a phase transition. And so quantum systems can actually tolerate a finite amount of noise. Yeah, so by now there are like literally hundreds of papers which study these phenomena in different systems. What we wanted to do with further is a bit different. So I have one slide in Russian, but I don't like it. I actually already prepared some clear space. So very often measurements are actually good. So they allow you to do stuff with the quantum systems. And one such thing is quantum teleportation. So imagine that I have Alice and Bob, and Alice has some unknown quantum system, some unknown, sorry, she has a qubit in some unknown state. Let's call it alpha 0 plus beta 1. Okay, and she, so let's call this time direction t, and she wants Bob to have psi. She does not know alpha and beta. She only wants she wants coherently move the state of this qubit from Alice to Bob. And they are not allowed to physically exchange this qubit. So they only can send classical information. Okay, so like one way to teleport things is, just to move physically this qubit from one lab, from Alice's lab to Bob's lab. But this is not what we want to do. We want to send only classical information, but we want to teleport quantum state. And this is actually possible. So in order to do this, it's important that Alice and Bob, they share a Bell state. So I prepare some Bell states, so 0, 0. Plus 1, 1. Okay, they share this Bell state. And this actually allows for the quantum teleportation. So, so there is this timeline of the Bell pair, and there is also a timeline of qubit psi. Okay, so the way it is done, it's the following. So Alice acts with a certain unitary operator on the state psi and on the one of the qubits in the Bell pair. Okay, and then she measures both of them. And when she measures, the outcome will be, one of the 4 possible. Yeah, the outcome will be basically 2 bits. So you can end up with qubits in state 0, 0, 1, 0, 0, 1, and 1, 1. So she measures them again in the Z basis. People often call it computational basis. So there is something happened here. Then she measured these 2 qubits in the Z basis, and then she just sent these 2 classical bits to Bob. Okay, just I don't know, calling him on the phone. And then Bob depending on these two classical bits, he performed another unitary. So this unitary V, it depends on these two classical bits Alice sent him. And it turns out that you can arrange for U and for V such that you end up with state psi here.
Sorry, what is C1 and C2? I mean,
okay, C1, C2 are just these classical bits here. So it's C1 is basically 0 or 1, what she measured for this state psi, and C2 is the outcome of the measurement of this of the qubit in the bell pair.
Yeah, but like the unitary transformation depends on how many parameters in that case, on two.
It depends on okay, there are like 4 possible V. So there is
V.
So U is the unitary transformation here is
matrix, right? It's a 2 by 2 matrix or 4 by 4.
So here V acts on 1 qubit, so it is it's 2 by 2 matrix, but you actually have 4 matrices. So you have so suppose Alice measured her qubits and she ended up with qubits in states 0, 0. Then she will send 0, 0 to Bob, and Bob will apply 2 by 2 matrix, which I call V 0, 0. If she measured 1, 0, she will send 1, 0, and Bob will apply another density, another 2 by 2 matrix, and so on. So there are 4 different 2 by 2 matrices depending on the measurement outcome. And she needs to supply this information to Bob in order for him to actually choose the right V. Okay, I can actually tell you again as an exercise what is U and V. So okay, so this is a bell pair.
So sorry, so U doesn't depend on psi, so it's kind of for every psi.
Yeah, for every psi. This protocol, it succeeds for every psi. And this is like the punchline. You don't need to know the state in order to teleport it. So this is state psi. So you need to apply so-called C0 gate. So what does C0 gate mean? So it means the following. This is what people call C0. It means that if I have 0 here, then the state should I write this down? Let's call this A. So C0, it does the following. If this what is called control control qubit is 0, nothing happens to this state. So I should call this psi tilde. So C naught, it takes, it has a control and it has a state on which you actually act. So if the control is in the 0 state, then you don't do anything. If the control is in 1, then you do, you do negation. So you can, I'll leave it as another exercise, how to write it as a 4x4 matrix. So this is the definition of C naught. So if control is in 0, you don't do anything. Otherwise, you negate this other qubit. Then you act with what is called H. So H is it's a 2x2 matrix. It's a simple one. A 1 1 minus 1 1. Okay. So, and here you perform measurements. So I leave it as an exercise, for you you start from some state psi, which is alpha 0 plus beta 1, and basically you perform these two operations, and like even on this slice, because this this is a maximal entangled state, so this is a Bell pair again, so this is 0 0 plus sorry, I think my laptop froze again. Okay, am I back?
Yes.
Can you hear me?
Yes, you're back.
Yeah, so okay, maybe I should just leave you here that okay, here it's 0 0 plus 1 1. Because of that, when you do all these operations, you actually end up here with a state very similar to the original psi. It just there will be some extra phases. So like typically you on this stage, this qubit will be in a state, for example, of this form. And then you need the measurement outcomes just to fix this relative phase between 0 and 1 at this stage. Yeah, yeah, this is the most simple quantum teleportation. I think it was first discussed in 1993 by Bennett and collaborators. But since then, people discovered any types of teleportation and so on. So the main idea is that you use classical communication in order to move. You use classical communication and existing entanglement. This is very important in order to move quantum states. So you basically, this is only possible because Alice and Bob, they already shared some entangled pair. So any questions? Okay, let me now move to basically the to my talk. So as I mentioned before, there were lots of discussions of measurement-induced phase transitions. So they are usually abbreviated as MIPT, and MIPT is also the English name for Moscow Institute of Physics and Technology, I mean, FISTECH. This is why we thought further that we have to write a paper on this. So as I said before, the upshot is that quantum systems are resilient to noise, and it takes a finite noise rate, to move to a different phase. But what I want to say is measurements are often important, for example, in these quantum teleportation protocols. And in the context of holography, there are two protocols, Gao-Jeffreys wall and Kitaev-Yoshida, which has been studied before. I'll explain what they are. And the question I would like to ask, okay, if we use these teleportation protocols at a finite rate, so they also include measurements, and what if I try to do this quantum teleportation at a very high rate? Are there any phase transitions? And so we used SYK as a toy model for this, and the answer is yes, there will be a phase transition. And as some of you know, SYK is dual to two-dimensional gravity. And the two-dimensional gravity, it will be a transition from to black hole phase to an eternal traversable wormhole phase. So I will explain what these words mean. So this is our motivation to see if there are any good measurement-induced phase transitions when teleportation is actually what you want. So are there any questions?
Does it fit with the claim that in condensed matter, this measurement-induced phase transition can be identified as C equals 0 conformal field theory? At least there is such claim in the literature that the measurement-induced transition is just non-unitary C equals 0 conformal point.
So I think here we studied SYK, so at the boundary we don't even have an extra dimension. So we only have time. So I think in this case actually it is we did not really look at the critical point. So unfortunately I don't know what is the critical behavior in our case. One comment I have though is I'm not sure if the C equals 0, because actually in this volume law phase, or rather, okay, let's look at the critical point. You do get indeed entanglement scaling, which is logarithmic, which you expect from CFT, but usually in CFT this coefficient is C over 3. And this coefficient here is non-zero. So if it is like in some sense, it can be zero central charge, but there you still have logarithmic scaling of entanglement. So this coefficient is not vanishing. And actually, this emergent quantum error correction picture can explain this as well.
Thanks.
So the plan for today is the following. I will first explain what these Gauss-Jeffreys wall and Kitaev-Yoshida protocols are. Then I will discuss Gauss-Jeffreys wall protocol. It is almost a MIPT because in fact the dynamics is unitary. You can interpret it as having measurements, but in fact it's unitary. But it will allow us to develop some important techniques, and then I will use it to an actual Kitaev-Yoshida case, and where you actually have a dynamics having measurements. So this is very similar to the story of Alice and Bob having maximal entangled state. But here I start in a slightly different state. So suppose Alice and Bob, they share some entangled quantum system, but it is not in a Bell state. It is what is called thermophile double state. So I have some Hamiltonian H. I prepare two copies of my system, left copy and right copy, and I form the following state. This is sum over the energy eigenvalues of a single system. So time goes up. I will follow SYK convention and denote physical time by U. Don't ask me why. It's what people use in SYK all the time. And this system, I assume that they undergoes the dynamics according to Hamiltonian, which is H left plus H right, such that the two systems involve independently. And as usual in quantum field theory, if I want to probe causal structure between different subregions, I can study commutator of bosonic operators or anti-commutator of fermionic operators. And here, there is no causal connection whatsoever, because, I mean, Alice can be on Earth and Bob can be on Mars, and they, despite the fact that they are entangled, they cannot really send any information between each other. So this anti-commutator of fermionic operators, one is located on the left and the other one located on the right, it's identically zero. So this setup, when I have two such entangled states, I can study. I can imagine that this Hamiltonian I'm studying, it's actually Hamiltonian of some holographic system. Okay, and so this then will be the boundary picture, but I also have, I can also lift it to I can add extra dimension and ask for corresponding gravity solution. And it was argued by Maldacena, Susskind, and others that this thermophile double in holography, it is dual to the so-called Einstein-Rosen-Bridge solution. So you can have a Schwarzschild black hole, but you can also study it maximal extension. So this is the so-called Kruskal solution. And Kruskal solution, it contains two universes which are connected by this Einstein-Rosen bridge. Yeah, this is one universe, this is another universe, and this is time slice. And one feature of this Einstein-Rosen bridge that it grows with time. So outside the black hole horizon, the metric looks like Schwarzschild black hole and it's static, but actually inside inside black hole it grows. So at later time, these two universes are connected by a much longer bridge. And this bridge grows. And it grows with the speed of light. So in fact, it is not possible to traverse this Einstein-Rosen bridge, because if you jump inside, you will not be able to cross it, because it expands of the speed of light, and you cannot really move faster than the speed of light. And for people who are familiar with Penrose diagrams, this is the Penrose diagram. So like it's characterization of space-time where lines at 45 degrees correspond to light geodesics. So this is one universe, this is another universe, this is the interior, and you see that you cannot reach the other side. If you jump inside, at best you go parallel to the expanding Einstein-Rosen bridge. So you cannot cross it, and in the end this bridge becomes very, very thin, and you end up in a singularity. So one way to probe this growth of the Einstein-Rosen bridge is to study this two-sided correlator. So this is not an anti-commutator. This is just a Whiteman function evaluated at equal times. And in fact, in this case, like for example, in the CFTs, this correlator will decay exponentially with time, where this exponent it's the effective temperature of the black hole solution. So this is the usual expectations in holographic theories, and you can prepare just the usual 1+1 CFT in this in such a state, and this will be the answer for the correlator. And you can also study SYK, and the correlator also behaves in this manner, so it exponentially decays. And the anti-commutator is identically zero just by construction. So now we actually want to add some, as in this picture with teleportations, we want to add measurements or any kind of interaction between the two sides in order to actually send information from one side to the other. And one of such protocols is Gauss-Jeffreys wall. Well, in some sense stupid, it says that let's just add an extra interaction between the two sides. So they involve independently with two Hamiltonians, but I also add an extra term in the Hamiltonian which couples the two sides. Okay, so the evolution is in fact is unitary. Another more elaborate protocol, which is Kitaev-Yoshida, it's when I pick up a subsystem on each side and I project it on the Bell state. So here it is not a measurement, it's a projection. So it involves post-selection. I will talk about it in detail in a few slides. But it's important that you don't just measure, but you also keep the outcome which you like. That if you perform a measurement and you end up in a state which is not Bell state, you throw this sample away. So you actually, in condensed matter, people call it forced measurement, or I think in high energy people call it projection, when you keep only one of the outcomes. And in fact, the diagnostics of teleportation, it's this anti-commutator between operator on the left and operator on the right. So you can actually map this anti-commutator to of how well you can transfer quantum states from left to right. So in my talk, order parameter, if I may call it this way, for the phase transition, it will be the value of this anti-commutator at certain times. So I want to make it as big as possible.
Sorry, may I ask? So this triangle called bell, does it mean that you reduced your the size of your Hilbert space, or I'm just misunderstood?
No, you don't. You keep this good. So it might be slightly unfortunate drawing. You project it on a bell state, but then you keep these qubits inside. Yeah.
And you always, I mean, on each step you always keep the same amount of states. So you
the dimension of the Hilbert space does not change.
No, I mean, taking this bell procedure, it applies only for like pair of states or for any number of states. I mean, in principle any, yeah. So I can select a bigger subsystem. I see. So
and
all
I can
in principle they can even be different. So you just
Oh, on left on the right it has to be they has to have the same size, but in principle it can be big.
I see. Thank you.
So from, say, just boundary perspective,
sorry, and this bell, it cannot be represented as an action of some exponent of something. It's not. I mean,
good. I will get to that.
Okay.
It's a very good question. Yeah, I will get to that. Yeah, from purely boundary perspective, this is pretty obvious that once I couple the two systems, the anti-commutator will be non-zero. Say, imagine that you have two harmonic oscillators, right? They are initially non-interacting, and then you added like a small interaction between the two sides, right? Then, of course, you will have a non-zero anti-commutator now. But what is interesting is in all these teleportation features that even if this coupling is small, this anti-commutator can become large. So, and a few years ago, I think it was 2016, when people first discussed Gauss-Jeffreys wall, the interesting holographic thing about this is that Gauss-Jeffreys wall interaction, how does it work in the bulk? It slows down the expansion of the Einstein-Rosen bridge. So in fact, when you introduce an operator on the left and operator on the right, it will send negative energy inside your gravitational system. And gravitational negative energy will slow down this expansion such that you can actually go inside the black hole horizon and then go outside on the other side. Because there's Einstein-Rosen bridge does not expand with the speed of light anymore. So like this Gauss-Jeffreys wall, it's only interesting from this perspective. And maybe some of you saw it in the news. There were a paper 2 days ago in Nature by Jeffreys and collaborators who implemented this protocol in an SYK model using some Google quantum device, Google quantum processor. And they implemented this teleportation protocol, and there was lots of hype in various.
Yeah, but there are only 7 probably Majorana fermion. I mean, they use only 9 qubits.
Yeah, it was just 8 qubits or something. And I mean, for me, the interesting thing about it is they implemented SYK on this. Strictly speaking, they did sparse SYK, but still, so the SYK model, the non-trivial thing about it is that it contains all-to-all interaction. So it's pretty impressive that they actually managed to implement this, on the existing device. So SYK model, here it's written very schematically. It's in some sense the simplest model ever. So you have some classical disorder, say J, I, J, K, L. So each index runs from 1 to n. Dot n. And you have some Majorana fermions. And J, it's a disorder with certain Gaussian distribution. So instead of 4 Majorana fermions, you can study Q, any even number Q. And here I also have a left system and right system. So you can, if you want, you can use Jordan-Wigner transformation and map Majorana fermions to spins. And then you just have super non-local interaction between spins. So this is the SYK model. Yeah, it has been studied to death. And in the Gauss-Jeffreys wall case, I also introduce an extra interaction between the sides. For example, this extra coupling, it can be psi I left, psi I right, for example. Or I can take this squared. So just some operator on the left and operator on the right. So this model looks complicated because I have quartic interaction, I have disorder. But long story short, in low energies, so and at large n, this model can be reduced to basically one effective degree of freedom, one classical effective degree of freedom. So with the following effective Hamiltonian. So L is some bosonic variable. Without the interaction between the sides, it's just the particle and the exponential potential. And you study trajectories, classical trajectories in this exponential potential, and you can map it to correlation functions. So I don't want to describe all this in detail, but what you need to keep in mind is it is basically a standard fact by now that this SYK with the two sides in the thermophile double state, it reduces to one effective classical degree of freedom. So and for that you need large n, and your temperature, which is 1 over beta, it has to be much smaller than J, but not too small. So it has to be larger than 1 over n.
Sorry about this effective Hamiltonian. First of all, until the time is turned, I mean, the interaction is turned on. I mean, you need to have at least two collective variables.
Sorry, what do you mean?
I mean, you have two non-interacting Hamiltonians.
Yes.
Why should I describe them using only one variable? I mean, if there is some reduction for one of them, I need to have the similar one for the second one.
Yeah, I think this is something like center of mass of them. So one of them.
Yes,
yeah, but initial theory is nonlinear. I mean, very nonlinear.
It's right. It's the center of the mass. Yeah. So I assume that there is left-right symmetry between the two. So it's right. There are two. Yeah, good catch. So there are indeed two degree of freedoms, but one of them is like symmetric, which is L, and the other one is antisymmetric. And I for simplicity, I study only the case when there is a left-right symmetry, so that this other degree of freedom is not really showing up.
Okay.
Yeah, and
also here it's not important. Doesn't important that delta is like smaller than 1 or greater than 1, the dimension.
no, here it's not. So here delta can be anything. So delta is determined by the operator you choose, but it for my discussion it can really be anything.
So delta is something like the number of fermions in O, right?
I think it's important. I mean, it's important that it's less than 1 because you have for some certain value of mu, you have a bound state in this effective Hamiltonian with.
Yeah, let's see. Yeah, I think delta should be less than 1. Yeah, for what I want to say. Yeah. Okay. Yeah. Let's say delta is less than 1.
Yeah, because in our work, I mean, we have studied the similar Hamiltonian from SYK, but for another reason, and all transition was based on the bounded state of this Hamiltonian or of similar Hamiltonian.
Okay. Yeah. Yeah. I guess what I'm going to say next, delta should be less than 1. Yeah, and basically, yeah, what I want to say is that I want to study the quench dynamics in this model. So I started initially with 2 non-interacting systems, and then I added mu term, and then I added it and I keep it on, and I ask what happens at various values of mu. And this reduction brings this problem in the form of high school mechanics problem. So I have initial exponential potential, and the trajectory is such that L runs away to infinity. Okay, this is the expansion of the Einstein-Rosen bridge I told you before, that you should think about L as the length of the Einstein-Rosen bridge. And it runs away to infinity very fast. Now I added this mu term, and now suddenly the potential looks like this. So it actually has some bound states. And when I do this, of course, my velocity and L will not jump. So I will, but my energy will, my effective energy will jump because I'm changing the potential. And then depending on how big mu is and at what point in time did I switch on the potential, I can end up with positive energy. So if the initial energy was positive and mu is very small, then obviously this new effective energy, it will be still positive. So that the trajectory will run away to infinity again. But if mu is large enough, I will end up with negative energy, and the trajectory will be trapped. So Einstein-Rosen bridge, it will not expand to infinite length. It will always have finite length. So it will maybe oscillate. It will be like I don't know what's the English word, accordion. So it will just oscillate back and forward, but this length will stay finite. And this is basically the transition we discovered. So I have a picture for this, but for the sake of time, I don't want to go into the detail and some picture of the correlation functions. But the main idea is if you switch on mu and mu is small, then nothing interesting happens. This correlator will eventually decay exponentially to 0. But if mu is large enough, this correlator, it will start to oscillate, because this effective variable L, it will be now trapped. It will not run away to infinity. So any questions? Let's see. I think I'm already over time, but I think I just need maybe 15 minutes to explain Kitaev-Yoshida, and then we'll be done.
Of course, okay.
So yeah, one small comment is that people actually expect a similar behavior in higher dimensional black holes. So what Gao-Jeffreys-Wall did, they did perturbative analysis in mu in like higher dimensional BTZ black hole, and they saw that this wormhole becomes traversable for a short amount of time. But what we're saying is that in JT gravity, you can actually find the full solution, and there is a phase transition when mu has a finite value. And people expect this to happen in higher dimensions as well. It's just very hard to show that. Okay, let me now study Kitaev-Yoshida case. So people sometimes call this dynamics of projection non-Hermitian or non-unitary, and I really don't like this because it kind of makes you worried if this dynamics is actually physical, but it is physical. So I just like to call it non-Hamiltonian evolution. So how would you implement this protocol in the lab? So you consider some time step du, and with this probability, you just leave your system alone. You don't do anything. This defines this parameter kappa. So this is now this Kitaev-Yoshida protocol when I do projection on the Bell state on the left and on the right. So this is, I'm now discussing this picture. So yeah, with certain probability, I don't do anything. Otherwise, I pick a random subsystem, a J from each side, and I measure it in a certain basis. And if I don't like the measurement outcome, then I throw away that prepared sample. And I start from the beginning. So I imagine that I prepare like 1 million samples. Every time step, I either don't do anything or I perform measurement. And if the system ended up in a state which I like after the projection, I keep this sample and I continue with the evolution. Otherwise, I throw away that sample. I have to throw it away because you know, in quantum mechanics, you don't have any control of what the measurement outcome is. So if you have some, you know, state which is spin up plus spin down, and you measure spin with probability 1/2, you will end up with in state up, and with probability 1/2, you end up with state down. And you have no control what is the outcome. You can only, you know, if you have many samples, you can only measure the probability of each outcome, but you don't have control of what outcome is. And here you need what is called post-selection. You perform a measurement and you only keep the outcome you like. So at the end of the day, if you started from 1 million samples and you did it many times, you might end up with only 2 samples. And the kind of the rule of the game is that even if you end up with 2 samples, it's all right. You will measure observables only in these 2 samples. So you suppose only 2 samples survived this post selection, and you want to measure some observable O in this in this ensemble, and so you will measure it in only 2 remaining samples, and you will, you know, divide by 2 because you only 2 samples remained. So this is such dynamics and can be described by non-normalized density matrix rho tilde. It's non-normalized because the number of samples it's decreasing with time, so its trace is not 1. And so at the end of the day, you evaluate your observables this way. So you evaluate these trace as usual, but also you divide manually by the trace. So this, in principle, it's very tedious, but this can be physically done in the lab, and people done this on some cold in cold atom experiments. So there are these two-step dynamics. It's represented by this equation. So at time u plus du, with this probability, you don't do anything. So it's just you left this sample alone. Otherwise, you're picked up one of the subsystems. So in this case, it's a Majorana fermion on each side, and you perform this projection. And here I also omitted the usual Hamiltonian part. Okay, maybe I should pause here because it's a lot, but this is the protocol which was discussed before by Kitaev Yoshida, and this is what we studied in SYK.
Is it possible to think about it as a kind of Lindbladian evolution?
Yes, yeah, it's Lindbladian, but it does not really have Lindblad form because Lindblad preserves trace, but this thing does not preserve trace.
I see.
But it is still a nice dynamics in the sense that it preserves hermicity and positivity of the density matrix. It just does not preserve, doesn't preserve the probability in a sense because you're throwing away, your lab samples. Okay, there was a question if I can represent it as some exponent, and it's a very good question because you can take this equation, so this is an exact equation, and you can do a number of approximations. I don't really want to go inside the details because we have a whole section in our paper discussing this, but the answer is yes. It's actually it's always nice to have some evolution operation in the form of the exponent, and you can indeed argue that you can approximate the above dynamics by such an exponent. So you use mean field approximation, and also you drop some dissipative terms which does not do anything to the entanglement but only generate energy, and you end up in this very nice form that then you have an anti-commutator in the time evolution. So S is this operator, and now you, instead of the Hamiltonian commutator, you have anti-commutator with a Hermitian operator S. And it's indeed equivalent to an extra Euclidean evolution in this form. So as a Hermitian operator, so this operator is non-unitary. In some, we called it soft projection because, with the usual projection, you either send state to 0 or you keep it as it is. Here, you either keep it as it is or you multiply it by some number less than 1. So this is a soft projection. That you don't project all the way to 0, but you decrease the amplitude. This is a good operation in the sense that you should check that it preserves hermicity and it preserves positivity of the density matrix. And a very similar coupling was studied some time ago by these authors. And we can actually compare it with the coupling we had before. So if this I previously studied this interaction when I just added a term in the Hamiltonian, and O left can be psi and O right can be psi. And in this sense, what I studied before, it was the same operator as, but it was in the Hamiltonian. But now it is not in the Hamiltonian. It has this extra anti-commutator structure. So this is the main approximation in our paper, that we indeed approximated as some exponent. So let me now explain how do you study such evolution. So you need Schwinger-Keldysh techniques for that. So if you have a normal evolution of the density matrix, you have a forward part and backward part, because you multiply rho with a evolution operator from left to right. This is the origin of plus and minus in the Schwinger-Keldysh notation. In our case, a forward part has exponent of plus kappa as du, and backward part will also have the same operator here, so that it preserves hermicity. So I cannot, you see, I cannot just do analytic continuation from mu to I mu, because the evolution on the plus contour and minus contour is actually different. So in fact, I will have two Hermitian conjugate operators on the plus contour and minus contour. So and you have to study these dynamics when you have a different effective complex Hamiltonian on plus and on minus. But the Hermitian conjugate, this is why they preserve the overall hermicity of the state. So I again can do this approximation when I reduce to 1 degree of freedom, L, but now we'll have L plus and L minus. So some wormhole length on the plus part and wormhole length on the minus part. And this operator is exactly the same operator I studied before. So I again have e to the minus 2 delta L. And as you know, Schwinger-Keldysh contour, it closes up. So what I really want to evaluate is something like this. So I start in thermophile double state. Then I act with my U. So I do evolution. And then when I evaluate an observable, I also put trace in there. So trace actually means that Schwinger-Keldysh contour, it closes up. So at the time when I evaluate my observables, L plus has to be equal to L minus. Okay, so this is one boundary condition. But U is not unitary. So in the usual Schwinger-Keldysh, you know, plus and minus parts, they cancel out if you don't have any operator insertions. In our case, it is not true, because you are kind of you have this non-causality coming from the fact that you know that you will project on a certain state in the future. And so for each t, you have to find the trajectory from scratch. So, but you basically have, instead of a Cauchy problem, when you start from initial state and you just evolve forward in time, now you have boundary condition in the future. Well, not in the future, but at the time of evaluation of your observable. And you have a boundary condition when you glue to the initial state. So is this clear? So yeah, and L is, in general, it will be complex, but when I actually evaluate the observable, it will be real. So it's because at the time capital T, it's L plus has to meet L minus, so they are complex conjugates, so they meet each other on the real line. So this is basically the dynamics what I want to study. So I have two complex conjugate Hamiltonians, and they are the most important boundary conditions that L plus has to meet L minus, despite the fact that they are complex. So now what is interesting is that for delta greater than 1/2, not 1, but 1/2, nothing interesting happens. So these trajectories for L plus and L minus, they just run away to infinity again, and the Einstein-Rosen bridge grows. However, for delta less than 1/2 and large kappa, there is a critical point in this complex plane of L. So of course, this is the effective potential, and it has critical points. It's a holomorphic function of L plus, so it has a critical point which is neither minimum or a maximum. It's a saddle. And so phi is minus L. So here it's this is plane of minus L, and there is this critical point marked red. And that what happens that for large enough kappa, the trajectories, they start to spend more and more time near this critical point. So you start from thermophile double, then you very quickly go to this unstable saddle point. You spend a lot of time near it, and then you go to the real axis in order to meet with, your plus minus partner. And such behavior, it only happens for delta less than 1/2. For delta greater than 1/2, the trajectories, they're not sensitive to the presence of the saddle point, and they just run away to infinity right away. But for delta less than 1/2 and large kappa, the saddle point, despite the fact that it's a saddle, it attracts the trajectories, and they spent a lot of time together. So this is a kind of the characterization of a new phase. So if you quench kappa and kappa is small, your trajectories will run away to infinity. But if kappa is large, then you will spend a lot of time near the saddle point. And for example, you can study the behavior of this 2-point function. So this is you can as I mentioned before, there is a one-to-one correspondence between correlation functions and the solutions for L. So here I plot L as a function of time for different initial temperatures. And basically, if temperature is high, so the strength of kappa, it's relative to temperature. So for high temperatures, L will just grow linearly with time. So this is the growth of the Einstein-Rosen bridge, at the speed of light. So it's L just grows, and this correlation function decays exponentially. But at lower temperatures, when effective kappa is large, this correlator actually it stops decaying, so it becomes a constant. And this steady state is actually independent of the initial temperature. So this part of the trajectory between the initial state and this red point, it depends on the initial temperature, but this part of the trajectory between the red point and the real axis, it doesn't depend on the initial state. So this steady state, in the steady state, this left-right, it has a constant value. It doesn't decay, and it also means that this commutator between left and right, it will be large. So you can check that I don't want to go into the detail, but yeah, this is what happens. You basically this is the fact that you have an eternal wormhole because its length of the Einstein-Rosen bridge stops growing. Yeah, and okay, maybe I can maybe I can just end with this, and if people are interested, I can also go over the open questions and so on. But this is basically our main result, that these projections, it's some non-Hamiltonian evolution, but it's capable of supporting this exotic phase of SYK, which is dual to an eternal wormhole, eternal traversable wormhole.
Okay, thank you. So question, please.
Alyosha, what will happen with, when we consider SYK? There is some feature that there is non-zero entropy at zero temperature. What will happen with this phenomena at this phase transition?
It's a good question. Let's see. Yeah, with the usual Gauss-Jeffreys wall, when you add this interaction, so you are basically asking about the ground state, right? So yeah, when you have Gauss-Jeffreys wall and you add this kind of interaction, then in the ground state you don't have this residual entropy anymore.
Yeah, I know. Yeah, but in your case,
my case, it's a little hard to think about it because you know, the dynamics is again non-Hamiltonian, so you cannot really say what's the ground state. I think it also should disappear. Based on what you expect from holography, because you don't have a horizon anymore. And also, in fact, and from the boundary perspective, this is not, it comes from evaluating G sigma action on your solution, right? And the solutions here, they are very similar to the solutions in the Gauss, in the Smaldasana-Shi case. So I think it should disappear, but I haven't done any calculations.
Okay, thanks.
I probably have naive question. So basically, to what extent have you basically using this knowledge, relation to black holes, or this is just kind of guiding principle and you don't need it actually to compute things?
Yeah, I don't really need it all. Like an SYK, really all I needed is this effective Hamiltonian for the length. But then I can just interpret it as a certain gravity solution, but I don't have to.
And also, I'm probably also stupid question. Speaking of, I don't know, of whatever, I don't know, implementing this protocol, these two protocols in real life, which one is, I don't know, better, or probably this phase transition might be treated as some abstraction for doing something, whatever. I'm just naive.
Okay, good. Yeah, so in fact, like 2 days ago, people implemented the left one, Gauss-Jeffreys wall, in real life. but they didn't study the case of large mu. So they only implemented this case with small mu. So they I think inserted just a few extra unitaries here. So they didn't switch it on for a long time, and also mu was small. But in principle, it can be done with no problem in a lab, because you just add an extra unitary. Okay, this is very easy to do. The one on the right, it's doing this in real life. It's a disaster, because you have to you have post selection, and it means that you have to prepare many samples of your systems. Then you measure, and then you keep only one of the outcomes. So it's as time goes on, the probability of actually having a sample which you invert for a long time, it decays exponentially. This is why these measurement-induced phase transitions, they are like very hard to implement in the lab. But what people want to study now, and there are more and more papers and literature on that, is what is called quantum feedback. So doing projections, as I said, is very hard, but what you can do is you can do kind of fix your state. So suppose you're basically have the same protocol as I said, as I used before. So with certain probability, you don't do anything, and otherwise you do a measurement of this operator, psi left, psi right. It has eigenvalues plus minus 1. So if you end up in a plus 1 case, this is what I had previously. But if you have a minus 1 outcome, then previously I was throwing away that thing. Yeah. But now I say, okay, it ended up in a minus 1 state, and I don't want to throw it away because I don't want to prepare my sample again. And instead, what I can do is I know now the state. I now know the state of where it got projected, and it's a wrong state. It's a minus 1 state, but I know what it is. And then I can act with an extra unitary in order to fix that. So I act with an extra psi. So psi, it's my run operator, and in fact, it's a unitary operator. And I do this. So this can be implemented in the lab. Again, I don't see any big abstractions for doing that. So previously, like in what I studied before, it was just these two terms. Yeah, and this was not preserving trace because I was throwing away another outcome. Now I don't throw it away, but I add an extra fixing unitaries. And yeah, what we want to do now with further is to study this case. So, and I think in measurement-induced phase transition literature, people started to discuss such setups as well because they are more experimentally realistic. So people call it quantum feedback because what I do to the system depends on the measurement outcome. So if I end up in a minus 1 state, then I flip it to be in plus 1 by virtue of this extra psi left operator. And now this is this row, it doesn't have a tilde over it because in fact you can check that this evolution preserves trace. But the problem is that we have not managed to rewrite this kind of evolution in this nice exponential form. And this is some abstraction for studying this model analytically. I think in this case, you have to do numerics. But we're still thinking about it.
Mm-hmm. Thank you. So any other questions, please? Okay, if not, then stop the translation. So thank you.
Thank